Okay, hello again, class. So now we are moving on to Newton's law of gravitation, and this is the base equation from which our gravitational force near or our gravitational near Earth's surface is based off of, and how we get that value of 9.81 times or meters per second squared. So that's how we. This is how we get the value. So we have Newton's law of gravitation published in 1687, and it's stated as follows. Every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. So if we take those two things, we say that this gravitational force is going to be proportional between the two masses, so directly proportional, and then inversely proportional between the distance. So now, in order to get rid of this alpha or this proportional sign here, we can say that this is going to be equal to g, which is our gravitational constant. This is different than little g. This is big G. So the gravitational constant was measured experimentally, and and we derived it using a very fancy experiment with lasers and large masses in between them. So this is called the Cavendish balance, which is used for determining the value of G. Go ahead and look at the figure in your book if you need clarification on what this actually looks like. And so let's go through. So that's how we determine the value of G, and we have determined that G is going to be equal to 6.67428. You can keep going, but usually you can cut it off here and say that this is times 10 to the negative 11th Newton meters squared over kilograms squared. Just know that when you plug in G, these units will cancel out with all the units here in order to give you a force in newtons here. So you see that the two masses cancel with the kilograms there, and the r squared cancels with the meters squared there, and it gives you newtons. So very often we've been asked, so why are these gravitational forces important? And they're basically what holds our universe together. So that's why they're important. But moving on, we talk about weight now, and so the weight of a body near or the weight of, when we're talking about weight in this class, we usually say that this is the force of gravity here, and this is directly equal to G me times m, which is your mass here, or the mass of the object that you're measuring, times the radius of Earth's surface. So what ends up happening is that the Earth is massive enough in this case where we don't actually have to account for how far you are away from Earth's surface for when you're near Earth's surface, because the radius is so large. And so this gives you what Fg is, and so then, but then this is, Fg is going to be, remember, this is going to be equal to, say, mg, and so then this is going to be equal to G me m over re squared, and so then G, the value of G itself, is going to be equal to G me. Your m's cancel over re. So very easily we can derive what the value of G is by taking the mass of the Earth, the radius of the Earth squared, and multiplying those quantities by our gravitational constant. So this is how we in fact are able to go ahead and measure the actual mass of the Earth, which is kind of incredible as we can't put the Earth on a scale. This is a little fun trick around how we are able to determine what this is equal to. So you do this little trick by saying that ME is going to be equal to GRE squared, because the radius of the Earth is much easier to determine than the mass of the Earth, all over your gravitational constant of G. And that's how we figured out how massive our Earth is. Moving on, this is also how we calculate our average density of our Earth, because since our Earth is a sphere, even though it spins at a rate that makes it a little longer at the equator and a little so it's more of an actually a oval. This is obviously really distorted, right? So with an axis that it spins around, right? But obviously this is a little distorted just to show you what it would actually look like around the equator. And so this is why we have different values for G, slightly different values for G at the equator and at the poles. So because you are a little farther away from Earth's surface at the equator than you would be at the poles, because the poles would be the minimum length that you'd be from the Earth's center. So then, comparatively, this RE value, or we should probably say this RE value here, is going to be smaller at the poles here, and so then you're going to experience different values of G at different points on the Earth's surface. But as an overall number, G is equal to 9.8 is a sufficiently good estimate for the types of problems that we are doing here. And so using gravitation, we can also estimate the volume of the Earth, because now we have, not because we can find the density of the Earth, not the volume, because now we have the mass, and the volume is derived from using RE squared. So then remember that since this is a sphere, VE is going to be 4/3 pi RE cubed. And then the density is going to be how massive the object is. So then we have to take ME, which is equal to GRE squared over G. We divide these two equations here. And so then all of a sudden the 3, so this is going to be rho E. This is an average density, because remember the layers of the Earth have different densities, because they are made up of different materials, like the crusts and the cores. They're different densities. So this is just the average density of the Earth. So be aware of that. So on the bottom, we're keeping our pi RE cubed. That 3 comes up, and we are obtaining another G here. And then on the top, we're going to continue to get our lower G, or our lowercase g, and then we still have RE squared. So that cancels with the 3 down here. And so then we are left with, let me just make this a little cleaner. We are left with 3G over 4 G pi RE. And this will yield you your density here. So if we are going to move on here, just know that since this is, we want to make sure that this is very, very clear to everybody. This is going to be an inverse square law. So this force is going to drop off proportionally to 1 over r squared. That's why we call it this inverse square law here. And so this can be this can be approximated here like this. So if we go off and we draw the Earth here, and then we can draw that this is going to be a force in Newton, or your weight in newtons. We can draw it like this. And so eventually, as R goes out to about, let's say, 30 times times 10 to the 6 meters, then we're going to start getting very, very, very small contributions or forces in between the in between these two bodies here. So if you think about it like this is about 0. So this is in newtons here. So this is going to be the max force that you experience near Earth's surface, and then as you slowly drift away here from Earth's surface, as your distance increases this way, this is what the force looks like as you drift away. So this is your weight, and this is R, or your distance from Earth's surface here. And so we're talking about the gravitational force between, we have a very large body and comparatively a very, very, very small body. So in these types of cases, most of the gravitation is being done from how massive our first object is and how close we are to that massive object. So things change obviously when you get to have objects that are extremely massive or even more massive than the Earth, comparatively to the Earth, and then the Earth becomes what we are to the Earth, if that makes sense. So if we're talking about the mass of the sun, the sun is orders of magnitude more massive than our little blue rock that we call home. And so then it's the same thing as how the Earth is orders of magnitude heavier than us. It's not the same, exactly the same, because we tend to be on the factor of maybe 100 kilograms at the most if we're talking about something that's over 200 pounds or 220 pounds, but comparatively to 5.97 times 10 to the 24th kilograms. But the mass of the sun is even bigger. If they have it here, it should be here somewhere. Okay, but we'll get back to that later. But moving on, now let's talk about potential energy here, because we've been talking about forces for a while, and we have to remember that potential energy is a very good way to map these. It's going to be very useful, and I'll show you why in just a second. So the amount of potential energy that in between two objects is going to be given by the work done to get from two different distances between those two objects. So in this case, you can say that W gravity. This is basically the same thing as we're talking about in a spring capacity. So the work done to gravity is going to be R1, R2 here of FR dr. And so then in this case, we're going to have that FR is going to be equal to our force due to gravity, and this is going to be negative GME M over R squared. And so then we're going to have this is going to be equal to negative GME M of the integral from R1 to R2 of 1 or dr over R squared. And so then very, very quickly, one thing that happens is this is negative R squared dr. So then this is going to be r to the -1 over -1. And so then we can just rewrite this as -1 over r. And this negative cancels with the 1 on the outside, so this is going to be g me m of 1 over r from r2 to r1. And so then this is going to give us g me m of 1 over r2 minus 1 over r1. And so then this is going to be our work, Wg. And so what we can do is we can compare equations with ones that we got earlier in other chapters in about chapter 7, and we see that then this appropriate definition for when say we take one of these guys out to infinity, and so we make R2 out to infinity and R1 is your starting point. And so we're bringing some object in from infinity. We see that u is then equal to g me m over r, which is the distance between the two objects. Okay, so remember that the work only depends on the initial and final values of r, not the path taken. So you can go in, you can take some silly path from an r here to say the Earth here. You can take any which way path, but the only part of the path that matters is the radial component of this. And so then this means that this gravitational force is a conservative force, and we see that it's independent of the path, which is a very keen observation that you guys are going to need for you'll see this again in 2020 if you guys end up moving up and taking that class. So this is conservative. And independent of path. And that's a very key point here. Okay, so more on gravitational potential energy. We did that. So now let's talk about motion of satellites in circular orbits. Okay, so moving on. We can start talking about how these satellites move and how we can talk about this motion here. So remember that so we have our gravitational force here, which is me m over r squared, and we can equate this to our radial force here, saying that this is going to be equal to mvr or mv squared over r here. And so we can do a couple things. We can get rid of the r's here, and we can get rid of these m's here. And so then we can say that v squared is going to be equal to g me over r. And so then we can very quickly get rid of that square root and just take it to the other side. And now we have our velocity for a circular orbit. And we see that the mass of the Earth is going to be constant, and our gravitational constant is a constant. That's just what it is. So for a satellite, because the mass doesn't actually depend on the mass, we can see that the velocity of the satellite is going to be just dependent on the orbit, assuming that there's no other forces tugging on the satellite. So So next up, we can start calculating periods of satellites, and just remember from our other ventures that v is going to be equal to this, and so then we can set these equal to each other. Square root g me over r, and so then we can start solving for t. Easiest way is to take t and move it to the other side and move this over, and so then we'll get g me over r is equal to t. And very, very quickly we can start to go ahead and simplify this. We can say that this is 2 pi comes out front, and then on the bottom you're going to have the square root of g over me, or g times me, and then you're going to have this r times r to the 1/2 on the top here. So then you can add these up, and very quickly you get r to the 3/2. And so then this is going to be your period equation. So now go ahead and we're going to have to talk about Kepler's 3 laws. And so this is talking about the motions of the planets. And we're going to go ahead and we have to talk about some different types of quantities here that we're going to have to go ahead and talk about here. So we have Kepler's 3 laws, and let me just read them off for you. So each planet moves in elliptical orbit with the sun at one focus of the ellipse. A line from the sun to a given planet sweeps out equal areas and equal times. The periods of the planets. So the first one was just with the sun at one focus of the ellipse. The second one was a line from the sun to a given planet sweeps out equal areas and equal times. And then the third law is the periods of the planets are proportional to the 3/2 powers of the major axes, lengths, and their orbits, or of their orbits. So so he saw that Kepler didn't know why these planets moved in such a way, but Newton went ahead and derived each of these laws, and we can see that now that Kepler's laws are consequences of Newton's law of motion and the law of gravitation. So this is how Newton put it all together. Even though Kepler came up with each of the 3 ideas, Newton went ahead and derived them mathematically. So one thing that we're really going to have to talk about is eccentricity, which describes, say, how elliptical the orbit actually is. And so they're talking about the geometry of these ellipses, and so the longest dimension is the major axis with half length a. So go ahead and you're gonna want to go ahead and look at the diagram here, because it's a tad difficult to draw. And so, but the eccentricity basically says, well, if E is equal to 0, then there's no eccentricity of the ellipse, and it's your ellipse is a circle. So your orbit is now a circle and not actually oval like in nature. But if you have, say something with a value of 1, then your ellipse is going to be very, very elongated and not circular in any way, shape, or form, or not even close. So I believe when you start to, I'm not quite sure about this, but I believe when you break that barrier of 1, there's a reason why it's limited at 1. So when you go over 1, your orbit breaks, and so instead of having, say, an orbit where, say, you have this here and this is your orbit, all of a sudden your orbit opens up when you have that eccentricity of over 1. And so then this is the equivalent of what it would look like if when you started to break your orbit in some way, shape, or form. So a couple of vocabulary words here. You have, okay, sorry, I had to sneeze. So these types of vocabulary words that we're talking about. So the point in the planet's orbit closest to the sun is the perihelion, and the point most distant is going to be your aphelion. So those are just two vocabulary words to go ahead and remember. And so even though these bodies are super far away from each other, Newton's laws still apply, and we saw that they can be derived, and you're not really given, say, an equation for your eccentricity here, but we can do a couple things with the next law, even though this is a little too. The mechanics involved in Kepler's first law are a little too complicated for physics 1710. So moving on to Kepler's second law here, we can talk about the area swept out by the orbit by any line the semi-major axis. So what we can do here is we can say that dA dt is going to be equal to 1/2 r d theta dt. And so I believe we have enough practice with rotational dynamics here that so basically what they say is, so say this is the sun here, and say that this is some time interval t around the short part of the interval, and this is the area, the two-dimensional area swept out by the orbit over this time period dt. Then they say that for a cone here, for the same time dt, then you have the same area inside this cone here, or this these two displacements. So when an object comes out here to this part of the orbit, it's going to slow down, and it's not going to cover as much arc length as it would over a certain period of time, even though it's still entrapped in the orbit. But this area here is going to be the same area as the this large area, even though, because this area here means that they're a bit longer arc length, but the radius to that arc length is going to be shorter. And so another thing we can say is that dA dt in this case is going to be 1/2 RV sine theta, or sine phi. We're just going ahead and taking what omega here is in this case, and we're just this is our sector velocity, and so we're just replacing this with some of our other quantities here. So one thing that you can see pretty immediately here is that we have RV sine phi, which is a quantity that we have encountered in other chapters, where this looks very, very similar to the cross product between R and V, right? Well, now just humor me for humor's sake, let's go ahead and multiply by m over m here. And so then we can distribute the m in here like this, and then all of a sudden, this quantity here, oh, look at that, would you look at that, this is going to be equal to L over 2m. So that's going to be our angular momentum stuck in there. So all of a sudden we have that this sector, this sector velocity here is going to be equivalent to the angular momentum of the system over 2m. And just remember that the angular momentum of this planet has to be constant. As we can take this one step further, and we can account for torque and just remember that this is going to be constant, and I have to remember to put my vector hats here. This is going to be constant in magnitude here, but angular momentum of this system has to be conserved. So either so when it gets out here, it's going to act different than if it was up close because of the time difference. And we've already derived Kepler's third law here, but this is just, we have to replace some of our quantities. So remember that this is going to be our period here, and this is going to be equal to 2 pi, and then we replace r with the semi-major axis, or the major axis here, over 3/2, and then this is going to be equal to g ms instead of me. So then this is going to be this period here. And so you would just go ahead and replace a with what Earth's major axis, and then all of a sudden we have our period for how long it takes to travel once around the sun, and we know that that is 365 days and about a fourth. And then we account for that with a leap year at the very end. Okay, class. Today we're going to continue our discussion from the other day about gravitation, and now we're going to talk about spherical mass distributions. So for any mass distribution with some spherical symmetry, with say some shell, and say that this shell has some density, and then this shell has some density, and then this inner core has some density. So this is going to be 3, 2, 1. So what we know about spherical mass densities and these shells means that all of this mass is going to be the same as if we took this as one whole object, right, with some average density rho bar, and we concentrated all the mass at the center of the sphere, and then use this as the radius here. So it's going to be the same exact equation here. This density, these three densities are going to be equivalent to these two. So this is going to be interchangeable. And we can go ahead and prove it. And we can go ahead and we can do this like your book does it. So what ends up happening is they say that a point mass outside some spherical shell has a potential energy of Ui is going to be equal to negative g m mi over s, where s is going to be the point from which this is going to be measured. So then we can prove this geometrically. And so if we have this here, say, and so then this is going to be some point P, this is going to be our origin, this will be our side S, this will be R minus R cosine phi, and this will be R cosine phi, as this is R, and this is where our mass is going to be located at, away from the origin. Okay, so what we can do is we can now sum up all of these particles over, say, a ring. So what we're doing is we're considering a ring on the surface of the shell, centered on the line from the center to the shell, or of the shell to M. And so then we do this because all the particles in the ring are made up of the same distance, s, from the point mass M, and using one of our equations from earlier in the chapter, the potential energy is given by this, and then so we just plug in, we are given by this, and then we have to plug in mi and s into this equation to get our potential energy. So what we're going to do here is we're going to sum up all of these, by saying that du is going to be equal to the sum of ui. And so this will just give us the sum of negative gmmi over s. And then we can see that all these are all going to be constants here and not affected by the sum because they're summing from I to I to n for how many particles there are. So when you do this sum for mi here, we're just going to get that this is going to be equal to negative gm dm over s. And so next up, we need to know the mass dm of the ring. We can find this with a little geometry. So if the radius of the shell is r, and so in terms of the angle phi is shown in our figure here, the radius of the ring is r sine phi, which we have here. And its circumference is 2 pi r sine phi. We just multiply it by 2 pi. And the width of the ring is r phi, and its area is approximately equal to its width times its circumference. So in this case, we can now say, or we can now go ahead and say that dA here is going to be equal to 2 pi r squared sine phi d phi. And the ratio of the ring's mass to the total mass of the shell is equal to the ratio of the area dA of the ring to the total area 4 pi r squared of the shell. So we just have to take this quantity and divide it by 4 pi r squared. And this is a big R, not a little r. And so then we get the pi and the r's come out. This is equal to 1/2. And we get that dm over m is going to be equal to sine phi d phi over 2. And therefore, what we can do with this is we can say that then dm is going to be equal to this. So we just multiply it out. And so now we can plug that into our equation here. So let's do that. And so then we get that du is going to be equal to negative g m over s times dm, which is going to be sine phi m d phi over 2. Okay. So one thing that we have to do here is we have to do a little integral over the whole sphere as phi varies from 0 to pi this time. This is not going to be from 0 to 2 pi. So we have to integrate this, and we have to do another integration over s here. And one thing that we can say about s is that s squared here is going to be equal to r minus r cosine phi. It's a little hard to see. So we're taking it from here, and we see that this is r sine phi and r minus r cosine phi. And so what we're going to do is see this is going to be our first term that's going to be squared, and then this term here is going to be our second term that's going to be squared by using the Pythagorean theorem. So this is our second term, this is our first term over here. So 1, 1, 2, 2. I know it's blurry over there and hard to see. Okay. So next up, what we can do is we can now this is a useful equation because if we take the derivative of this or the differential of it of both sides, what we're going to end up getting is we're going to get ds 2s, which is what we have here. And so what we can do is we can substitute this equation now into this one. So let's finish our differential here. We're going to get 2r cosine, or no, we're going to get sine phi d phi. Okay, so now we plug that in here, and I'm going to get rid of this. And so now we're going to have that du is going to be equal to negative g m sine phi d phi. And what we do is we take, this is going to be 2s is going to be equal to 2r capital R sine phi d phi divided by ds. And so then we have to take the inverse of this. So then we're going to get a ds up here, and then underneath we'll get a 2r sine phi d phi down here. So our sine phi's cancel, and now we're going to get negative g m ds over 2r r. Okay, so now what we can do is we're gonna integrate ds, and so then we're gonna get u on this side, and we're gonna integrate from r plus r to or from r minus r to r plus r. And so GMM and the 2 come out. So let's stick them out here. If you guys can see that. Yeah. Okay. There we go. Yeah. GMM over 2 comes out. Or no. Yeah. This is all for ds. So that those extra r's all come out also, and this is just over ds, which gives us, this is equal to GMM over 2r capital R times r plus capital R minus r minus capital R. Okay, so first things first, let's do what this gives us. And so this should give us, this will be a positive R, that'll be a negative R, or that this will be a negative R, this will be a positive capital R. So these R's are going to cancel, and these R's here are going to double up, and we'll get 2R out of this. And that'll cancel with this R, and that. And that will yield us negative G M over the radius R. And this is our regular result for our potential energy for just 2 masses in space. So we see that for some spherical mass distribution that we return to these same answer. So next thing that we have to talk about is a point mass inside of this shell. So say that there's some hole inside of our object, and now one of the popular ways of going about this problem, or illustrating this problem, is you bore a hole straight through the center of the Earth, and you see that your potential energy is going to be is going to be a function of the radius within the shell. So where you are with respect to the origin in that case. And so our proof ends up being slightly different, as from before we had that that little r was the first variable, and now in our integration the big R is going to be our first variable. So in this case u is going to be equal to negative g over 2r capital R integral of ds from r minus little r and r plus, or big R plus r. So then this integral now gives us, this is going to be negative g m over 2r, and then you just have to say that this is going to be r plus r minus r in this. And so now these r's are going to cancel out, and these two are going to double up. So you're going to get 2r, so that's going to cancel with that, and that's going to yield negative g m little m over r. So now we have big R here for a point mass inside a spherical shell. Okay, so journey to the center of the Earth. Let's do this now. So imagine we drill a hole through the Earth along the diameter and drop a mail pouch down the hole. Derive an expression for the gravitational force Fg on the pouch as a function of its distance from the Earth's center. Assume that the Earth's density is uniform. And obviously we saw that this is not a realistic model, but we're just assuming it for the sake of this question. Okay, so in order to do this, we have to say, okay, value of Fg at r is determined only by the mass within a spherical region of radius r. And so we have that Fg is then going to be gm m over r squared. And then we have to replace big M with what its value is, and so then we'll get, this is g m over r squared of me r cubed over r e cubed. And so then this is going to yield that our force is going to be g m over radius of the Earth squared or cubed times r, which is going to be your radius from the center of the Earth. And we obtain this here by doing something similar to what we did before to find what dm was, by saying that the overall mass m divided by the mass of the Earth would be 4 pi r cubed, oh, this is 4/3 pi r cubed over 4/3 pi r e cubed. And then obviously these factors cancel out, and then you get that m is going to be equal to me times the ratio of these volumes. And that's how we get this here. Okay. So next up we have to cover apparent weight and the Earth's rotation. So because the Earth rotates on its axis, it's not an inertial frame. So technically all the physics that we've been doing is not true. Not that it's not true. It's a good two-dimensional approximation, but there's also since the Earth is also spinning underneath you, there's there's another fictional force that acts upon objects that stay in the air for a long time. And so eventually the Earth will spin underneath those objects. And we call that the Coriolis effect. There's many, people pronounce it so many different ways, but that's how I say it, Coriolis effect. Saying that it's a force is not really accurate, because it's not really a force. It's just a consequence of the Earth rotating underneath an object. There's no actual force doing any work on the object, but it's still moving in that direction because of the Earth's spin. Okay, but coming back from my tangent, we'll talk about apparent weight now. And okay, so we're talking about apparent weight because the Earth is indeed spinning. So when you're considering how fast you're spinning on an object, you consider that, say you take a spinning ring and you want to measure the force of F radial that pulls you inwards, and that adds to your gravitational pull. So what ends up happening is that at the poles of the Earth, you're going to end up having the same apparent weight because you're just spinning in place. You're just merely rotating. But when you're on the equator, you're going to there's going to be more of a force that is going to go ahead and change your apparent weight. So we have to talk about using acceleration of or your radial acceleration to account for this. So I think I mentioned this in an earlier lecture, that your weight is not always the same based on where it is or based on your latitude. So what we're going to do is we're going to say that our W naught minus this F is going to be equal to our centripetal acceleration here, and this is going to be the radius of the Earth down here. So at the equator, you're going to have you're going to feel the full force of this radius RE, because if we're talking about the Earth here, and this is its pole and it's spinning like this, then at certain points, so at the equator here, this is going to be your RE, but at this point here, this distance here from the pole is going to be, or the axis of rotation is going to be less than it would be at, say, the equator. So your apparent weight is going to change as you move in this direction and as you move in this direction. So this is where your weight is going to be the same, and this is where it's going to be, I believe it's going to be less. Okay, so we can go ahead and start to derive this. And so at this point here, we're at the equator, we have that W is going to be equal to W naught minus MV squared over RE. And then G, in this case, dividing out the mass of yourself, we are going to get G is going to be equal to G naught minus MV squared over RE. And so then for any distance of latitude here, we have that this is going to be your angle theta here. And so then this portion here is going to be your new distance here, and this is going to be what we say is, so this is RE at any point, and so then we're going to have our hypotenuse, and we want to find our adjacent, which means we use our cosine. So then we have that our R is going to be equal to RE cosine theta, and this will be your R at any point. And so then you can see how if we plug that in here, how this value changes. And so as cosine goes to 90 degrees, eventually this equation will become zero. We'll have to take the limit as it goes there in order to get rid of the fact that this is going to be a zero on the bottom of our fraction. But as we take the limit as it goes to zero, then this entire equation here will eventually go to zero, and so then you're just left with your value for gravity, and when this goes to theta is equal to zero, then we just get RE, and so then you'll get your value of R at the equator. And so this can be used for any of these values of theta in between these two. And so that's how you account for your apparent weight here. Okay. And now we'll talk about black holes briefly using Newtonian mechanics. So what we're going to do is we're going to derive the period and the Schwarzschild radius or Schwarzschild radius, whatever you prefer to pronounce it. And so what we're first going to do is we're going to find the escape speed from a star before we can talk about black holes. So the density of a star is going to be equal to m over v, which just gives it the mass of our star over 4/3 pi r cubed. And you can plug in values for any star here. The book uses our sun as its example star, and now we want to talk about the escape speed. And so for our escape speed, we found that for the surface of a spherical mass m with radius r is going to be v is equal to, this is from earlier in the chapter, 2gm over r. And so then we have to plug in what m is going to be, and m is just going to be equal to our density rho times our volume v. And so then we get that v is going to be equal to 2g over r times m, which is going to be rho times 4/3 pi r cubed. And so simplifying this equation, we get that this is equal to 2, or this is going to be equal to 8/3 g rho pi, or I'm going to just put the pi next to the 8 pi. Okay, and then we get one of our r's cancel, so we get r squared here. And so since this is a square, we can take this out of the square root, and we just get that this is times r. And so there you go. So you plug in our gravitational constant and the density of our sun, and then you will go ahead and get the escape speed from our sun. And this value is going to end up being like 1/500th of the speed of light. And we see that this value for escape speed is going to be independent of the mass of the body. And so this is why black holes are so interesting, is that black holes have these things called event horizons, and once you cross the event horizon, you cannot cross back. So that's why we say that black holes are so dense that that light cannot even escape from this. so what we're going to end up doing is we have to find the critical radius of these black holes or these entities. And so what we're going to end up doing is if we set V now equal to C, then we can see that we don't need a massive object in order to find what this. So a black hole can have a mass that is not infinite in order for this to, or this equality to work. All it has to do is we have to find the critical radius at which light can no longer escape. So what we can do here is we can just solve this equation for R itself. And so what we can see here is we can go ahead and solve this for R. And so what we're going to end up getting is when we set this equal to C, we'll just solve for R here. Okay, we're not exactly solving for R here, but what we're going to do is we're going to take this equation and set it to C. And so then from here, we have to retrieve R out of this equation here. So then we get C squared on one side is equal to 2G M over R. And we'll swap the R and the C's places. And so then we get that RS is going to be equal to 2GM over C squared. And so what you can do is you can plug in what M is here at this point. And so then we can say that M is going to be equal to rho. This is going to be rho over, or times 4/3 pi r cubed, pi r squared. And now it's no longer a function of mass. One last thing to note for this chapter is I believe the 15th edition was written before the discovery of the picture of a black hole, and it looks just about like what we thought it would look based on our computer simulations. And if you guys haven't seen that picture, which was posted on April 6th of 2019 by, I believe, Brianna Bauman, I would go ahead and look that picture up, because it is quite awesome that we now have our first picture of a black hole. All right, have a good day, guys.